So as you know, it is St. Patrick's Day, and I'm doing my best by wearing green. How do you like it? Nice green shirt. I hope everyone else is out there wearing green. What do you mean it looks like Halloween to you? It's a gorgeous shade of green. Bought it especially for today. So, what do you mean Halloween? Just the floating head. I don't know what you're talking about. Where was I going to go with that? I'm a little worried though, because I don't know if you've been following the news or you're taking political science or social studies or whatever, and they talk about cultural appropriation. Well, you know, this is truly an Irish tradition, so you got to wonder, what's the deal here? Is this going to be considered a very bad thing to do? So away we go. If anyone really cares and wants to see what I look like, I can of course confirm to you that I am wearing green. See, there you go. That's the color, that's what you get. And with the magic of technology, I can make sure that I consider, here I am, celebrating St. Patrick's Day with you. And further to that, if I were to go this, we can do other things. So for example, what we have here, by the way, is the announcement I have for today. If you received an email from me yesterday, this applies to you. If not, just pay attention. I've been working on the presentation schedule, and the way that it was being set up is you've signed up for lab classes. Excuse me, L1, 2, 3, 5, 6, 7, and 8 are the ones you signed up for. I have tentatively put you in your lab class because hypothetically you have that time free to give your presentation. However, the problem we have is that there are too many students in sections L1 and L2 and L7. The maximum number of students that can present on a given day is 9. So I sent an email to the students in L1, L2, and L7 asking them to please, if it is at all possible, for them to switch. And of course you can see here that L4 was added and L9 was added, and there's lots of space in each of those sections. If we can, of course L6 has space available too. If the students that are in L1, L2, and L7 have the ability to present in, well, even L3 and L5, you can add 1 or 2 more students each of those. It will get the numbers down. I need between 8 and 9 students per section in order to evenly distribute it out. The other option, if that doesn't work, is that if there's more than 9 students or more than 18 students over the 2 weeks, I'll just actually, because the labs actually do go for 1 more week, we'll just hold that 1 lab section to go for a 3rd week. So there's an incentive to jump into other sections. If you do have the ability to switch, and please send me an email. Please send me an email and I will gladly move you in. And for everybody, once I get the numbers to something that's reasonable, I will be informing everybody when their presentation is going to be. I already told you, if you're in any one of the other lab sections, you'll be presenting during that lab section. It will be a random order of presentation with one exception. If a student volunteers to go first, I will let them do that. There are some students that prefer to go first, and there's other students that are terrified of it, but if a student prefers to go first and get it, quote, over and done with, I will let that occur. But other than that, after that, you are randomized in your presentation order. What do you mean, Afrin? Umesh could never. Umesh could never do what? I need to put me back where I belong. So I'm mixing a couple holidays up. So where are we at? We are done with that. Please send me an email if you can switch. I might send another email in a couple of days just reminding people. And then everyone will get an email once I get the schedule sorted out. To remind you of what we did last day, we finished off with this example right here. Oh, the presentations are the week of April 5th and 12th. So those 2 weeks. And if I need to, they'll go the next week to the week of the 17th as well. So week of the 5th and 12th. With regards to this course material, last day we finished off looking at this, and I just wanted to remind you of the results. So we have the mole fraction in the liquid, and we calculated the mole fraction in the vapor phase. And we had entity A and B. In the liquid phase, it was 0.40 mole fraction B, and that was 0.60 mole fraction A. In the vapor phase, this became 0.21, and this became 0.79 mole fraction. And that led to this observation. And that observation was that the vapor phase always has a higher mole fraction of the more volatile entity than the liquid phase. So the vapor phase has a higher mole fraction of the more volatile entity than the liquid. And we just saw that with the example that we just did here. Where does this take us? It introduces a very, very important property, industrial property, called fractional distillation. I just said the vapor phase always has a higher mole fraction of the more volatile entity than the liquid phase. When we apply that to a boiling solution, the distillate, the stuff that evaporates and gets condensed somewhere else, contains more of the volatile entity. So, the distillate contains more of the more volatile entity. And repeated boiling of the distillate, so you boil something, you collect the vapor. You boil the vapor, you collect the vapor again. You continue to do that, and we end up results in separation of the entities to the point that you can actually take a mixture of volatile entities and separate it into pure A or pure B in general. There is one exception that's right down here. When you're boiling something, if the boiling point changes, the liquid is a mixture. If the boiling point changes, you're always giving off more of the more volatile entities, so the composition changes, the boiling point's going to change. If the boiling point is constant, the liquid is either a pure liquid or it's something called an azeotrope. And we'll talk about azeotropes in just a few slides. So this is the liquid vapor phase diagram. And in this example right here, what we have is X, that's our starting point. X is about a 30% mole fraction B. The boiling point of X is right here, okay? When it boils, the composition of the vapor has this composition here. So the vapor composition curve takes it up, and you see it going up to this point, and what condenses is this mole fraction here. So it ends up condensing with this composition, which is more about 0.56 mole fraction B. So it went from about 0.3 to 0.56. If we now boil the vapor and condense the vapor, the composition is at Z, which is about 80%. So if continued repetition of this ends up giving us closer and closer to pure B. And so on this vapor phase diagram, 1, 2, 3, 4, 5, 6 or so steps in a fractional distillation end up giving us pure B in the solution. That's the power of fractional distillation, is that we can take a mixture of stuff and we can, through a series of distillation steps, get pure compounds out. Applied industrially, refineries do this. They take in crude oil down at the bottom here. So crude oil comes in right there. That crude oil comes in and it is heated up. And the more volatile entities end up rising up. So the boiling point as you go up goes down, it goes lower and lower and lower. But as things vaporize, each one of these columns is effectively a fractional distillation step. So things condense at around 400 degrees Celsius. If they stay a liquid, they're extracted off, and that's between 20 and 70 carbon atoms, and that's ship oil, heating oil type of idea. If they continue to boil at 400 degrees Celsius but condense at 350, C20 to 50, that's oil. Oils, waxes, polishes, that type of idea, and so on and so forth. 270, 170, etc. If it continues to boil through all of these steps, it stays a gas, and methane, ethane, propane, and butane are gases at room temperature, come off, and now you can do further processes to separate them. So if you're happy with C20 to 50, you're good. You've got this, it's lubricating oils. If you want to further fractionate this, you can separate it down such you get narrower bands of molecular mass hydrocarbons. This is one application of fractional distillation. About azeotropes. So the one thing that this diagram here has is that the vapor composition curve has a minimum at pure A and a maximum at pure B. That is what an ideal solution would give you. A minimum at pure A and a maximum at pure B. If the maximum or minimum exists somewhere between A and B, you produce an azeotrope. An azeotrope is a mixture with the same composition in the gas and liquid states. So, and what that means is if the composition is the same in the gas and liquid states, we can't actually separate azeotropic mixtures by distillation. So, for a lack of a better example, this is actually a really good example. It shows major deviation from ideal behavior. And so we see a minimum in the vapor composition curve at around 67% mole fraction benzene. So starting with X at 10% benzene, we go up and over. The vapor is no longer 10% benzene, it's around 42% benzene. And when you do that again, you get, by about 3 steps, you get to the azeotropic position. And you can't do anything once you're at the azeotropic position. If you were to start on the other side of it, start with 90% benzene, you go up and over. The vapor that condenses is now 75%, and it basically another 2 or 3 steps, and it ends up at the azeotropic position as well. When you have a non-ideal solution, you can potentially have an azeotropic solution formed. If you've been following along through my notes, and I hope you are, and I hope you're reasonably paying attention, you'll know that I've been using ethanol and water, alcohol, for a lot of the examples. It's something that most people can actually relate to. I couldn't use that as an example here before because ethanol and water actually forms an azeotropic mixture, so it fits here. This is the vapor phase diagram for ethanol water mixture as a mole fraction of ethanol, and what you see is that at about 94% you end up having a minimum in the vapor composition curve. So at 94-95% ethanol, you can't get any purer to pure alcohol. You have to use other chemical means to remove the remaining water. And that's possible to do, it's just, it requires a different step. So ethanol water forms a phase diagram at about 94% ethanol. Does anyone have any questions before we about these vapor composition curves, vapor liquid phase diagrams, before we carry on? The hands are amazing. All right. The last concept that I want to look at in this chapter is that of colligative properties. Colligative properties encompasses three main aspects: osmotic pressure and boiling point, freezing point changes. So those are the things that we're going to look at for the remainder of this chapter. In the context of colligative properties, they're a class of properties of a solution that only depend on the amount of solute. They don't care what that solute is. It could be ions, it could be highly charged ions, it could be other organic or not inorganic molecules that are dissolved in solution. As long as it forms a solution, so sucrose or glycerin or sodium chloride or iron chloride or iron bromide, anything that can dissolve in solution will impart colligative properties to that solution. There's a couple of things here. I'm actually mixing a little bit together. Why 1410 is separated from the discussion on osmotic pressure, I don't understand. I'm integrating it here because everyone else does. And there have been a few changes to the examples as well. So when we get to some of the examples, my examples, well, once I was writing out the solutions, I realized, oh, that's not correct. And so there's been a few changes. All right. So what is osmotic pressure? If you have a concentration gradient, you have a net flow. So ignoring osmotic pressure for now, imagine getting a coffee at Tim Hortons, for lack of a better example, where they don't mix it, so there's a really high concentration of sugar on the bottom, and the top is basically pure coffee or tea, whatever it happens to be. It wasn't mixed. If you were to let that sit for a long period of time, what's going to end up happening is that the sugar, sucrose, is going to diffuse upwards. There's going to be a diffusion from the high concentration to the low concentration area, and the solvent is going to diffuse down into that high concentration area. So solvent diffuses down, the sucrose is going to diffuse upwards. The end result is, after a period of time, you have a uniform mixture, uniform solution. The reason for that is entropic. Now, we haven't touched thermodynamics yet, that's next unit, but the mixing is a purely entropic phenomenon. The point is that there is a drive or an energy to get a uniform solution. Here we have down at the bottom the same idea. We have a glucose solution on the right-hand side and pure water on the left-hand side, and they introduced this idea of a semi-permeable membrane. Semi-permeable membrane is something that allows only the solvent molecule to pass through, but not the solute. So glucose is much bigger than water, so it won't pass through really tiny pores in a semi-permeable membrane. Even ions like sodium and chloride and whatever, they're all hydrated. So sodium doesn't float around as just a sodium atom. It's got 4 or more water molecules that are very tightly bound. And those water molecules don't come off. So that much bigger sodium ion or chloride ion cannot diffuse through the semi-permeable membrane. The end result is that in here, there's a net diffusion of the solvent, the pure water, in to try to dilute the right-hand side. And in the way that this is set up, it ends up moving the level of the water higher. So the level of the pure water solution goes down, the level of the solution increases to a point where there's now a pressure differential, okay, and that's called the osmotic pressure. And when you know what the osmotic pressure is, it means that the flow in one direction is the same as the flow of solvent in the other direction. And if you were to create this solution and you just let it sit, you can measure the osmotic pressure literally just by waiting and measuring the height of this column. Another way you can do that is you could literally put a weight down there, or a force down there, and that force keeps the two levels the same. And you measure how much force you need to apply, because that is the same pressure as the osmotic pressure. And if you keep the force level the same, the flow goes in the same in both directions. Either one of those processes will allow you to measure the osmotic pressure. Osmosis is the general phenomena that we're observing here. Osmosis is the process of the solvent molecules passing through the semi-permeable membrane to try and equalize the solute concentration. The example that's in the picture is that of going swimming. Your cells contain high ion and protein concentrations. The pool or the bathtub that you're in generally does not. Salt water, ocean water does, so this doesn't occur as readily in salt water, but in freshwater pools and in bathtubs, what you end up having is osmosis occurring as water from the pool or bathtub ends up diffusing into the cells, intracellular membranes, and it's trying to equalize the concentration, and you get those wonderful little wrinkles that exist on your skin. That's one example of osmosis. We have osmotic pressure that I showed in the previous slide that prevents osmosis by putting a force down. Can't do that for your fingers, but what you can do in terms of osmotic pressure is if you put more force, you're actually able to reverse the process. And if you buy drinking water, so if you buy drinking water, one of the types of drinking water you can buy is RO, reverse osmosis drinking water. It is generally the purest water you can get because the semi-permeable membrane generally only allows the solvent. Filtration allows some ions to go through, etc., etc. You can't get rid of sodium chloride with a simple carbon filter. You can with reverse osmosis. The way this is done, the picture that is shown there is that of a reverse osmosis system for an ocean-going boat, like a sailboat or a pleasure boat on the ocean. It breaks down, or you're doing a trans-ocean crossing, something like that, an ocean crossing. You cannot carry enough fresh water for what you need for the entire process trip, so you need to produce it en route. This is a hand osmosis, reverse osmosis water generator. So one tip goes into the ocean and you literally pump, and it produces 25-30 liters a day with a couple hours worth of work. And it is nothing more than a membrane down at the bottom. You put now salt water in the right-hand side, and that salt water just gets pressed down and gets pure water out. Then you replace the salt water and you do it again and again. So basically every pump has a new amount of salt water on the right-hand side to get pure water out. The greater the concentration difference, the harder it is. So you want to have fresh salt water every time. This is just one picture, but you can go online and looking up at reverse osmosis, you can find that there's actually some countries that produce their drinking water through major reverse osmosis plants that are close to the ocean. They bring in seawater from the ocean, they put it through very large pumps, the size of silos type of idea, and they put high pressure on them, and what comes out the other side is purified water. It's clean from contaminants, organisms, and even down to the things as small as the sodium and chloride ions. So some countries actually get their drinking water through a reverse osmosis process. Now, the example at the bottom here is different than what you have written down because I realized there was an error in your notes. So please note that it is quite rewritten from what you have in your notes. Osmotic pressure is very similar to the ideal gas law. Ideal gas law is, of course, PV equals nRT. Well, osmotic pressure is pi times V. Pi is the symbol given for osmotic pressure. is equal to I, which we'll talk about in a bit, and RT. So very, very similar. Realize that when you're dealing with a solution, N over V is just concentration, moles per liter. So we can replace the N and the V with this small caps M, which is molarity, the symbol for molarity. So what is I? I is called the Van 't Hoff factor. I never use the term. I have to look it up every time I think about it. But it is the number of discrete entities per solute entity. This should work. So for NaCl, I is equal to 2, because NaCl forms Na plus Cl minus ions in solution. For glucose, I is equal to 1, because glucose is still glucose in solution. For something else like calcium bromide, I is going to be equal to 3 because you have the calcium ions plus you've got 2 independent bromide ions floating around through solution. I noticed, yes, it's glitching. It's been glitching earlier class too. There's nothing I can do about it. I don't know why. And it is only glitching on the tablet. So something about the tablet, this is going to fix itself shortly. So we go from there. In the example that we have present here, we have the ions in blood are mostly sodium and chloride. And one of your problem set 5 questions actually confirms this for you. It's about 90% sodium chloride. We're going to assume that blood is about 0.92% sodium chloride by mass. That's the error in your notes. And has a density of 1.06 grams per milliliter. We want to determine the osmotic pressure at 310 Kelvin, which is normal body temperature. All right, so when I go over to the document camera, it's better if I don't talk and write, so I'm just going to do one or the other. So the first thing we need to do is we need to determine the sodium chloride concentration. We start with our 0.92, oh sorry, let me correct that just a tiny bit. 0.92% sodium chloride by mass. What I want you to remember is how I presented this for things like parts per million, parts per billion, parts per trillion. I'm going to do the exact same thing for percent by mass. This is .92 grams a solution over 100 grams, or sorry, 0.92 grams of NaCl over 100 grams of solution. That's 0.92% by mass. But it allows us to now do our conversions. And I'm just going to write down the conversions to give me moles per liter. So the first conversion converts to milliliters of solution, milliliters of blood. Then it converts to liters of blood. And then the other conversion leaves you with moles of NaCl. So you're left with moles per liter. Per blood or per solution, whatever. Now we can go through and calculate the osmotic pressure. We're dealing with NaCl. I is equal to 2. So here we have got the osmotic pressure calculation. I've just substituted in the Van 't Hoff factor of I is equal to 2 for sodium chloride, the concentration, the value of R that cancels my units out, and the temperature, and the end result is an osmotic pressure of blood of 8.6 bar, which is a substantial amount for a fairly low thing. Oh, good observation, Benjamin. We're dealing with capital pi. So here, let me just pick a color. We'll go with green. There is, of course, lowercase pi. This is going to come back. And there's capital pi. Lowercase pi, more squiggly. If you actually were to look at them on a computer, uppercase pi has, well, of course it's bigger, but it also has a straight top on it. Good question, good observation. Yes, we're also getting to a point where we're starting to reuse Greek letters many, many times as you carry on through a science degree. So you'll note the pi in pi v equals INRT or whatever is capital pi, not lowercase pi. Good question. That's how we calculate osmotic pressure. The calculations are simple. Concepts are a little bit more challenging here. The other colligative properties I want to look at are freezing and boiling point, and what happens when you have a solute dissolved in solution. When something freezes, the solid is pure solid. You generally don't incorporate the solute in the solid. So the solid is pure, the gas, the vapor phase is pure. You only see the solute in the liquid phase. So when I add a solute to a liquid solution, it doesn't go into the solid, it doesn't go into the gas phase, it affects the liquid. And when a liquid contains a solute, the local concentration, you can look at it as the concentration. If you've got a volume of liquid, some of the solute molecules, excuse me, have been replaced by, some of the solvent molecules have been replaced by solute. So what was a water molecule is now a sodium ion. What was a water molecule is now a chloride ion with the surrounding hydration sphere, water molecules bound to it quite tightly. What ends up happening is that the effective concentration of the liquid goes down. So in terms of crystallization, if you have less water molecules that can bond to the solid, less water molecules to form ice, the crystallization process is slower because the solute is removed some of them, it impedes the solvent molecules from bonding to the solid. The reverse process, fusion, is unchanged. In order to make the crystallization, the solidification process, faster, you need to cool the temperature down. If it's colder temperature, well then you're going to be able to increase the rate at which crystallization occurs. And once you do that, then you reach equilibrium. So a lower temperature is required to establish equilibrium when you have a solute in solution, and we observe that as a freezing point depression. It takes a lower temperature to cause something to freeze. Salt water doesn't freeze at 0 degrees Celsius, it freezes at many degrees below that, again depending on the concentration of salt. Now if we want to consider boiling, boiling involves both the condensation of the vapor down to a liquid, but also the evaporation of the liquid to form the gas phase. That evaporation is slower because the surface is not pure solvent. There's some solute molecules up there. So they impede the solvent molecules evaporating. But condensation is unchanged because the vapor only contains the solvent molecules. The net result is that because their evaporation is impeded, in order to increase the rate of evaporation, we need to increase the temperature to bring the vaporization rate back up. So in terms of boiling, a higher boiling point is required to establish equilibrium. And we observe that and call that phenomena boiling point elevation. So for the colligative properties, there's two. When you have a solution, freezing point goes down, freezing point depression, boiling point goes up, boiling point elevation. And all of this is related to the reestablishing of equilibrium that we have right there. The phase diagram is a little bit more confusing, but just realize that the freezing point goes to a lower temperature, the vaporization point goes to a higher point, simply to reestablish equilibrium. The lines are actually moved. That's the phase transitions of the solution rather than of the pure solvent. If the other explanation that we have here makes sense, that's fine. Just accept that. There is a change here in the calculations. I didn't have the negative sign in your notes, so please put the negative sign for the freezing point depression equation at the top. Again, the equations are pretty simple. This is how we calculate what delta T is for freezing point depression or boiling point elevation. And the data is tabulated. The Kf and the Kb are both tabulated values for a number of different solvents. And also convenient in this table is what the boiling point and freezing point are, so you can actually measure or calculate the actual temperature. So this is how we calculate how much comes out. Before we do a calculation, let's just look at a more common example, and that common example is your automobile, your automobile. The radiator could contain pure water. Completely possible, not in northern climates, but anywhere where it doesn't get below zero, it is possible that you could put pure water in the radiator and it would probably work just fine. However, in northern climates, we need to prevent the radiator liquid from freezing, so we add chemicals, and we are focusing on the freezing point depression aspect of the chemicals that we add. Ethylene glycol is the red, glycerol is the green, and propylene glycol is the blue line. And what we find is that there is a minimum in the freezing point at around a mole fraction between about 30 and 40% mole fraction of these polyols. The interesting part of this is that if you do live in a hot climate, and I know at least one of my students is in Arizona, and I haven't received a plane ticket to come down there yet, by the way. Anyway, ignore that. It also helps prevent it from overheating, because boiling point also goes up. Boiling point elevation is not as much as it is for freezing point depression, but you can see that in this 30 to 40 mole fraction range, you end up with about a 10 to 15 degree increase in boiling point. So in hot climates, it's still valuable to add antifreeze to your radiator because it's also anti-boil as well. Couple of things associated with this. Ethylene glycol, the red one, is the most common antifreeze used. It is most common, it's easy to produce industrially, except it is toxic. Toxic to humans, toxic to animals. It actually also apparently tastes sweet. So animals will drink it or eat stuff that is soaked in it. So rags or whatnot, they will suck out the ethylene glycol. It is very toxic and it does kill animals. Propylene glycol is non-toxic. If your family has an RV and they need to winterize the RV, they will buy the RV antifreeze, which is commonly colored pink. It's actually clear, but they add a pink color to it, and they use that. Propylene glycol, it tastes bad, but it's not going to kill you. So if there's a little bit of pink solution left over when you're starting up the RV in next year, that's fine. Propylene glycol is non-toxic to humans and animals. We are animals. Here's the two examples that I want to look at to finish off this chapter. I don't know if there's any changes to what's in your notes, but just make sure that they're the same as what you've got. We talked a little bit about adding salt to water to cook pasta, and the misconception, well, what I told you was that the misconception was that it was increase the boiling point. Well, now we have the ability to find out what is the boiling point of a saltwater pasta solution? And the recipe for this is to add about 1 tablespoon of sodium chloride to about 4 liters of water to cook pasta. So let's go through and do that calculation. And once again, very likely, the signal is going to go bad. I apologize for that. The first thing I want to do is I want to calculate, back up 1 sec. We'll come back to that. The thing that I forgot to mention with regards to this equation is that this is a carryover from the good old days. Concentration is in molal. Concentration needs to be in molality, not molarity. So that's what we actually need to do here. We need to actually calculate the molality of the solution, not the molarity of it. Okay. So that's what I'm going to do right now. "20 grams of sodium chloride, 4 liters of water." And the one thing I am doing is I'm assuming that the density of water is 1 gram per milliliter or 1 kilogram per liter. And you'll find that you have units of moles of sodium chloride per kilogram of water. So that's the molality of the solution. And molality is given the symbol lowercase m, which is confusing because it's sometimes mistaken for mass. It's molality. Because we're working with sodium chloride, the Van 't Hoff factor is 2. And molal and 1 over molal cancel. So the end result is you have a change in temperature of 0.087 Kelvin. And if you remember that delta T is T final minus T initial. The boiling point goes from 373.15, boiling point of water, to 373.24. It goes up an almost negligible amount. The change in boiling point as a function of altitude is significantly greater than this. So salting water to cook pasta does not appreciably increase the boiling point. What it does do is it adds flavor to the pasta. Oh, how did I get 0.51? Good question. If you go back and you look at the table that was on the previous slide, go back, there we go. What you find is that for water, Kf, the boiling point elevation, Kb, for water is 0.51. 373.51. And so I just looked up that value, and the boiling point is 373.15. I need to know it to more significant figures to actually make this value work. Okay? Good question. I've got 4 minutes left, and I do want to do this question, and I also want to talk about your term exam. So just that way all the notes are going to be together. So this next example looks at 1.55 grams of an unknown, non-volatile, non-ionic entity, increases the boiling point of 50 grams of benzene by 0.485 degrees Celsius. We're asked to determine the molar mass of the unknown, and that's what we're going to do now. And if you could be patient and hang on for a few minutes, I do want to talk about your term exam, which is next Wednesday. So appreciate that. Thank you. So for this question, we are given everything we need to know to calculate the molality. We have and so we're told it's a non-volatile entity, so that means I is equal to 1. Kb for benzene off of the table is 2.65 Kelvin per molal. And we don't know what the molality is. So we can figure out that M, through simple mathematics, is 0.183 moles per kilogram. Now, how many moles did we get? Well, we had 50 grams, or 0.50 kilograms of benzene. And so this expression allows us to determine that we have, I'll just put it over here, 9.15 times 10 to the minus 3 moles of our unknown. Well, how do we get molar mass? We have simply mass over moles is the fundamental definition of this. And so we end up getting the mass, which we can look at our problem. It was 1.55 grams of our unknown over 9.15 times 10 to the minus 3 moles, and that gives us a value of 169.4 grams per mole, limited to 3 significant figures. $169.4 grams per mole is the molar mass of the unknown. Prior to the use of technology like mass spec and instrumentation like that, this is literally how organic chemists determined the molecular mass or estimated the molecular mass. They would do freezing point depression or boiling point elevation studies on their unknowns. You make something in the lab, you go and test it, and this is one of the ways of it being tested. All right, that is all of the material in chapters 12 and 14. So this module is done. The talking head is back. So you have a term exam coming up. I will send this all out via email, but I'll say it to you now. The term exam is going to be everything from the last midterm to this midterm to the end of chapter 14. So that's chapters 16, 17, and 18, the rest of Equilibria, plus chapters 12 and 14. is what is going to be on the term exam. The term exam is next Wednesday. It's going to follow the same format as it did for the last one. There will be a few changes based on conversations that we have had and how to improve it and simplify it for you. Okay, maybe one question less, but I still want to try to push the time thing. But instead of having multiple uploads, you'll have one upload. So all of your files can be put together as one upload, and away you go. And with regards to problem set 5, because of your term exam next week, there isn't going to be a problem set quiz on problem set 5. The answers to problem set 5 will be posted this weekend, probably sometime on Saturday afternoon. And realize that I just created problem set 5, so there might be errors in the solutions, okay? It's kind of something I do like 10 p.m. till 1 a.m. So there might be an error or two. So if you get a different answer than what I have written down, send me an email to that effect, and I will see who's correct. And some of the times it's you, so please do that. Term exam 16, 17, 18, chapters 12 and 14. Answers to problem set 5 posted this weekend, and that's about it. The only last thing I want to close with is if you are in lab sections, 1, 2, and I don't remember what the other one is, and where there's more students than can be there, if you can switch into any of the other lab sections to give your presentation there, I would greatly appreciate you sending me an email, and the quicker we get that, the quicker I can send out the schedule for presentations. That's it, ladies and gentlemen, and we'll see you. Oh, Friday, we're going to start the chapter 13. Chapter 13 is on thermodynamics, so have those notes. It's not on the term exam, but we are going to continue with the course material on Friday. So we'll see you Friday. Take care.